So the next level of problems we'll talk about are mathematical problems from this chapter. So one of the types you will see is how to determine empirical formula of a compound. What's empirical formula? Empirical formula is the simplest ratio of element. Simplest ratio of element. For example, if we had a compound C6H12O6. This is the molecular formula of the compound and this is how the compound is represented. But if you were to represent the empirical formula of this compound, that would be CH2O. This would be the representation of the empirical formula of the compound, simplest ratio. So if we had a compound that contains nitrogen and oxygen, and when this was decomposed, 24.5 grams of nitrogen was obtained and 70.0 grams of oxygen was obtained. What would be the empirical formula of this compound? So for empirical formula, what do you need? You need mole ratio. Mole ratio is what you need for finding out empirical formula. So first, let's get the moles, number of moles, and then we will get the mole ratio. So how will we get the number of moles? 24.5 grams of nitrogen. We know from the previous chapter that 14.01 grams of nitrogen is 1 mole of nitrogen. So from here we get 1.75 moles of nitrogen. Same thing with oxygen. 70.0 grams of oxygen. From periodic table, 16.00 grams of oxygen is 1 mole of oxygen. So from here we get 4.38 moles of oxygen. So we got the moles here. Now we obtain the mole ratio. So how do we get the mole ratio? So if this were the compound, as we know now, so we would write it as 1.75 O 4.38. But obviously compounds are not written like this. They are written like this, right? NO2 or N2O, something like this, not with fractions. So how do we get the mole ratio from here? Choose the lowest number and then divide that number with divide all the moles with that number, meaning 1.75 divided by 1.75, O 4.38 divided by 1.75. What do you get here? You get NO 2.5. Now remember, we don't want decimals or fractions. So what do? We multiply this entire number by an integer. So we get whole number here. So I choose to multiply with 2. Why? Because 2.5 multiplied by 2 will give me a whole number. So N2O5. That is the empirical formula of the compound. Now given the empirical formula, say for example empirical formula is given to you, and how do you get molecular formula from there? Say for example there is a compound, empirical formula of that compound is C2H3O. Its molar mass. This is very important. It's molar mass. How do you get the molar mass? Molar mass is obtained by adding masses of all the elements that are present here. So I'll deviate a little bit here. So I'll do an example for molar mass. Okay. So how do you get molar mass of, say for example, carbon dioxide? Carbon 12.01 from our periodic table plus oxygen 16.00, but there are 2 oxygens, so 2 16.00. So this is 32.00 plus 12.01. So that gives us 44.01 grams per mole. Okay, so this is a deviation. I just did an example for this. Now molar mass for this particular compound in question was found to be, So one piece of data is that empirical formula is this. The second piece of data that we have is that molar mass is 86.09 grams per mole. Okay, so molar mass is the mass of the compound that you get from molecular formula, which is not equal to empirical formula. You need to understand that molecular formula is not the same as empirical formula. It might be same, but it is not same. Okay, it might be same or it might not be same. Meaning, for example, again I'm going to deviate here. So if there is a compound, again I'll go back to CO2. This is the simplest ratio. This is molecular formula of this is molecular formula of carbon dioxide. Now remember, this is also empirical formula because you can't get more simpler than this, right? So if you divide this by 2, you will get C 0.5 and O1. So this is not a simple ratio, right? So molecular formula can be equal to empirical formula, or sometimes it may not be equal to. So in our case, I'm just going to write this one more time. Empirical formula is C2H3O. Molar mass is 86.09 grams per mole. We have to find out what is the molecular formula. Okay, so if you were to relate empirical formula to molecular formula, empirical formula multiplied by a certain number is molecular formula, right? So what is empirical formula mass here? If you get the mass from this empirical formula molar mass, 2 times 12.01 plus 3 times 1.008 and 1 times 16.00. Again, I got these numbers from periodic table. So empirical formula mass, empirical formula molar mass, which I got from here, this will be equal to 43.04. Okay, 43.04 grams per mole, right? So 43.04 grams per mole multiplied by N is equal to 86.09, right? So what is N? N is 86.09 divided by 43.04, which will be equal to 2. So if empirical formula is C2H3O, molecular formula will be C2H3O multiplied by 2, which would be C4H6O2. That will be the molecular formula. Now another type of problem you will come across is, how do you get empirical formula from combustion analysis? What is combustion analysis? What is combustion analysis? A compound is burned in presence of oxygen, or compound is exposed to oxygen, and you get some products from it and analyze the products to figure out what this compound is. Okay. Now, any compound that contains carbon and hydrogen, or carbon, hydrogen and oxygen, when they react with oxygen, they yield carbon dioxide and water vapor. Carbon dioxide and water vapor. So one particular compound, so a compound that contains carbon, hydrogen and oxygen, 0.8233 grams of that compound on reacting with oxygen produces 2.445 grams of carbon dioxide and 0.6003 grams of water. Now, if a compound that contains carbon, hydrogen and oxygen, we take 0.8233 grams of it and make it react with oxygen, it produces 2.445 grams of carbon dioxide and 0.6003 grams of water. Given this information, what is the empirical formula of this compound? That's the question. So, 2.445 grams of carbon dioxide. If you think about it, how many moles of carbon dioxide is it? 44.01 grams of carbon dioxide is 1 mole of carbon dioxide. So this will come out to be 0.05556 moles carbon dioxide. Now in the same way, 0.6003 grams of water, when you convert this to moles, you're converting this to moles from grams, so you use 18.02 grams, which is the molar mass of water, which is equal to 1 mole of water. When you convert 0.6003 grams to moles, you will get 0.03331 moles of water. So then, now convert. We're not interested in moles of carbon dioxide or moles of water. We're interested in moles of carbon and moles of hydrogen because our compound contains carbon and hydrogen. So you take it one step further and we'll say 0.05556 moles of carbon dioxide. How many moles of carbon is it? 1 mole of carbon dioxide contains 1 mole of carbon. So this will be equal to 0.05556 moles of carbon. Now 0.03331 moles of water. How many moles of hydrogen is it? Every 1 mole of water contains 2 moles of hydrogen atoms because it is H2O, right? Every 1 mole of water has 2 hydrogens, right? So this will be 0.06662 moles of hydrogen. Okay, then what do? We have to convert from moles of carbon, 0.556 moles of carbon, to grams of carbon. Again, we're interested in grams, right? So 12.01 grams of carbon. This will give us 0.6673 grams of carbon. Same way, 0.06662 moles of hydrogen. Every 1 mole of hydrogen is containing 1.008 grams of hydrogen. These numbers we are getting from the periodic table. This is equal to 0.06715 grams of hydrogen. Now remember, along with carbon and hydrogen, there is also oxygen in this compound. So how will you do that? You take the entire mass of the compound, which is 0.8233 grams, minus 0.6673 grams of carbon and 0.06715 grams of hydrogen. So out of 0.8233 grams of the compound, some of it is carbon, some of it is hydrogen. What is the rest of it? Rest of it is oxygen, which will be equal to 0.0889 grams of oxygen. So from grams of oxygen, 0.0889 grams of oxygen, convert that to moles of oxygen. So 16 grams of oxygen is 1 mole of oxygen, which is 0.00556 moles of oxygen. So if you think about it, in this compound there is 0.05556 moles of carbon, 0.06662 moles of hydrogen, and 0.00556 moles of oxygen. Obviously, we cannot write the formula for a compound like this. We have to have whole numbers here. So what do? We take the moles of each of the compound and look at these numbers. Which is the smallest of all of them? Smallest is 0.00556. So 0.00556, 0.00556. All the moles we divided by the lowest number of moles because we want to get the mole ratio. And in this case, we will get C10H12O. So this is the empirical formula of this compound. Now the next type of question we will be looking at in this chapter is balancing equations. This is conceptual. Balancing equations. This is not very high calculations. Small divisions and multiplications will be involved, but mostly it is very less math. C4H10, for example, gas. When reacting with oxygen gas, yields carbon dioxide and water vapor. So this is the given equation and we have to balance this equation. So if you think about it, on the reactant side we have 4 carbons, 10 hydrogens and 2 oxygens. On the product side, we have 1 carbon, 3 oxygens and 2 hydrogens. 1 carbon, 2 hydrogens and 3 oxygens. So the atoms are not the same. Here we have 4 carbons and here we have 1 carbon. So now we have to balance this equation. So let's begin with carbon. So we have in this case 4 carbons, right? So since there are 4 carbons, let's place 4 here. Remember, when you are balancing equations, you will not be able to, you can only change the coefficients of all the compounds. You cannot change these numbers. The subscripts may not be changed because subscripts are a part of the formula. So you can change only the coefficients. So because we have 4 carbons here, let's place 4 here. Now we have 4 carbons on the reactant side, and we also have 4 carbons on the product side. So now carbons are balanced. Now let's balance hydrogen. So we have 10 hydrogens here and we have 2 hydrogens here. So to balance that out, let's place 5 in front of hydrogen. So hydrogen will be 5, right? And then, so 5 multiplied by 2, 10. So now we have 10 hydrogens and 10 hydrogens as well. So let's balance oxygen. So for this, we will need a little bit more space. So I'm going to another slide. Again, our reaction to begin with was C4H10 plus O2 yields CO2 plus H2O. And to balance carbon, we placed a 4 here. To balance hydrogen, we placed a 5 here. And going back and checking, on the reactant side, we have 4 carbons. Product side, we have 4 carbons. Reactant side, we have 10 hydrogens. Product side also 5 multiplied by 2. So this 5 will hold for this entire compound. So there are 5 waters. So 5 times 2 hydrogen atoms. So 5 times 2, which is 10 hydrogen atoms. 5 times 2, 10 hydrogens. Now we are left with oxygen. That is a little bit tricky here. What's happening? There are 2 oxygens in this case. And now here we have 4 times 2, 8 oxygens plus 5 times 1, 5 oxygens. So we have 13 oxygens on the product side. 13 oxygens on the product side. So to balance oxygens, what I will do is I will place this here in front of oxygen. I will place 13 divided by 2. Why did I do that? To make both of them the same number. So now if I do this, 13 divided by 2 multiplied by 2. So I have a 13 divided by 2 as a coefficient multiplied by 2. So 13 by 2 multiplied by 2, this will give me a 13 oxygen. So I have 13 oxygens on the reactant side and 13 oxygens on the product side. But of course, you cannot leave a reaction like this. So overall, now the reaction is going to look like this. C4H10 plus 13 over 2 O2 yields 4 CO2 plus 5 H2O, right? But you cannot leave a reaction like this. So what do? We multiply the entire equation with 2. So then you end up with 2C4H10 plus 13O2 yields 8CO2 plus 10 H2O. And if you go back and check, 4 carbons multiplied by 2, so that will be 8 carbons. 8 carbons. 10 hydrogens here, but overall we have 2, so 20 hydrogens. 10 multiplied by 2, 20 hydrogens. 13 multiplied by 2, 26 oxygens. 8 multiplied by 2, 16 plus 10. So that is 26 oxygens as well. And so this reaction is now balanced.